And then we come to the last topic we'll cover, the transformation of electromagnetic field. So last time we already uh, derived the forms of so-called covariant forms or expressing Maxwell equation in the tensor notation in the so-called covariant form. And so that is good. So that the whatever frame you have the same Maxwell equation, whatever inertial frame that. But there's also the question: if you know the field in one frame, how do you get the expression of the field in another frame? So, which involve a transformation. This transformation is different from uh, the the transformation of space-time that contains a transformation of four vector. Now the few are components of the four tensors. So you need to transform it like a tensor. So it's slightly more complicated. So we can start doing that. Uh, so the first step, of course, you just write down the general rule. So it's a tensor. The uh, field tensor is transformed like a tensor. So you want to express the f prime transform from the k frame to k prime frame as usual, your k frame, k prime frame, and we have velocity, relative velocity v, and along the x direction, and with Jackson in the electric field section, he changed that to x direction. In previous section, he used the z, so kind of a little confusing, but you just need to pay attention to what he used. Okay, so it doesn't matter actually. All right, so there's a relative velocity k prime relative to k in velocity v. So, but the form is the same, of course. You just transform it like according to the transformation rule of tensors. So partial x prime, partial x alpha beta gamma prime beta delta, and then transform the f. This is gamma delta. Okay, so the transformation rule is like that. So you know that these are just Lorentz transformation, and you know how to write it down. Then you can say that's the end of it, or you just whatever field you want to transform, you just do this multiplication. And the problem is that this multiplication is quite complicated because these are this 4x4 matrices. These two, so you need to do two matrix multiplication, and that would take a while to do it. And we try to go through it, and we see that it straightforward. It can be done if you are patient and just be careful, and then it can be done in a straightforward way. But obviously, it will just to write down the expression will take a while. So, you be better to do it once and get a formula, which is much easier to use. So that is what we try to do instead of just every time you just use that. Of course, if you put it in computer, then it doesn't matter. So you put this thing in just like a uh, com just so-called computing, just computer do the algebra for you. This is just matrix multiplication that is straightforward to do. But if you want a simpler formula, you need to go through this multiplication once at least. So what we'll do. So so first you want to write this as a matrix multiplication. So basically uh, this is like a matrix alpha and gamma, and sum over this gamma index is like a multiplication. So you write, just copy that, and then that's gamma delta. And then obviously you multiply this also like a matrix multiplication, but this is beta delta. So suppose you need to do a transpose to get delta beta. But in the case of Lorentz transformation, at least along the single direction, the the matrix is symmetric. So it doesn't matter whether you do a transpose or not. So you can either say just multiply by another Lorentz transformation, but because it's symmetric, is sum over delta n. Okay, so we can write it more explicitly. Just put a number. This the, the Lorentz transformation you probably remember now. Is, yes, yeah, so that's this one. And this matrix is the Chung-Sang field tensor. You most likely need to look it up. That's 11,137. And it's anti-symmetric, so it has 4 zero elements. Diagonal elements are 0. And then the 6th element here is this is minus ex, e sub x minus e sub y minus e sub b. And the column is this the negative of this row, so e sub y, e sub t. Right. Then the magnetic field are these here. It's a little bit difficult to memorize, but if you look that up, this should be b sub c minus b sub c. This is b sub y. This is minus b sub x. And likewise, this is the opposite, the negative of this. This is negative of this. This is the negative of that one. Okay, so that's the field tensor. And then you need to multiply it by Lorentz transformation. Okay. Just write it down, takes some time. Okay, so the rest is just matrix multiplication. So you have two means you have two multiplication. You can do either one first. Doesn't matter. It doesn't depend on the order. Okay, so we can do this multiplication first, right? There's 4 by 4 matrix multiplication, which looks difficult or horrible. But if you are patient, you can get it done in a straightforward manner. Just copy this one. Okay, and obviously the result would be also a 4 by 4 matrix, so we need some space, larger space for it to get the result. And you could just follow the usual matrix multiplication and get all 16 elements, work out that way. But for 4 by 4 matrix, there's the trick that you can separate that the 4 by 4 into 4 parts. And each matrix, 4 by 4 matrix, is treated like a 2 by 2 matrix with elements that are 2 by 2 matrices. So you have 4 2 by 2 matrices. So there's 4 elements. The elements are 2 by 2 matrices, and then you can treat it like a multiplication of 2 by 2 matrices into another 2 by. The result is 2 by 2 matrix, but elements are 2 by 2 matrices also. So like this element would be this matrix times this matrix plus this matrix times this matrix. Okay, is that okay? So you can do that. If you are not sure that you actually can do that, you need to spend some time think about it. If you are patient, you think about it, you realize that that's exactly the same. The two-way will give you exactly the same result. Okay. Uh, but we'll just treat it like what we already know this is possible. Okay, then we'll do that one matrix by at a time, one element at a time. And there are four of them, then we'll need to do all four of them because there's no apparent symmetry. There's some symmetry in individual multiplication, like this element is this times this plus this times that. Okay, and this is anti. This is odd. I mean, uh, this is uh, a anti-symmetric. So this your EX and minus EX. This is symmetric matrix. So that the result will be anti-symmetric. So so you only have the three elements, and this times that obviously is zero because this element, this matrix is zero. So you don't have to worry about this times that. Just this times that, right? So yeah, the four elements. The first element of this 2 by 2 matrix is this times this is zero, and this times that, which gives you gamma beta EX, gamma beta E sub X. Okay, and the next element, this one is this times this is zero, this times that is minus gamma and E sub X. Right, and obviously this one is anti-symmetric, so it's gamma E sub X, which is also very simple. You just multiply this by such that you know that gamma E sub X. Finally, this one is this one times this one, plus this one times this one, which is zero, so it's minus gamma beta E sub X. Okay, this not too bad. That's four elements. We got this matrix then. Okay, the second one, like this one, that's this times that, which is zero, and then this times that, which is easy. This is an identity matrix. We just copy this matrix to here. Okay, so not too bad. So, so like I said, you be patient and step by step. Some of the step would be easy, so you don't need to worry too much. Just follow the rule and do all the multiplication. This element is this times that, which is zero, and this times that, right? This is so this is just copy from this one, zero, x zero. Okay, the three of them are easy. And now finally this one will be slightly more complicated. It's this element, this times this plus this times that, which is zero, so that the second multiplication, okay, this is zero. But the first one is more complicated because there's no symmetry in this matrix. Although this is symmetric, there's no symmetry. So finally, there's no symmetry. You need to work out all four elements. Okay, so one at a time. So this one is this times this plus this times that. Okay, both have a gamma, so take a gamma out. So E sub y, and then minus beta E sub c. Okay, so that's the first element. This element is this times this plus this times that. Okay, and so both also have a gamma, and then the one without a beta is BC, so write this first, B sub C. This is now the second one is beta times E sub minus beta times E sub 1. Okay, the third one is times this plus this times that, and gamma is z, right? They both have negative signs plus beta is y. Okay, finally, this one is this times this plus this times both are negative, so both are negative gamma. And this b sub y plus beta b sub g. Right? If I want to check my analogy, so I got my somewhere along the line I may do some error. Okay, so just follow me. Okay, that's not too bad. So the first we're done with the first multiplication. Now we have the second one. Now the second one, you can do a trick that according to the symmetry, right? Because F itself is anti-symmetric, right? So this F is anti-symmetric. F prime should also be anti-symmetric. You can check that out by reversing the indices, and because these are symmetric, this is symmetric. You can work out that is anti-symmetric. So it means that like the F original F prime is also that's just have 6 independent elements, and also the in our case, if we want to again use the same trick, and get 4 of this element. So, because of this symmetry, we only need to work on 3 of them, right? Because like these two will be just like a transpose of the other one, negative transpose of the other. Okay, so that's not too bad. So this one and this one just refract it back. So you need to work out 3 of them. Okay, then let's try to do it. Among all these elements, this element will be the easiest because this is 0 times this, which is 0, and this times that, which is just identity. So just copy. Okay, so that's not too bad. And now let's work out the first one. This might take a little bit of work, but it's this times this one, and this times that one, which is 0. That's good. This is complicated. You multiply by 0, that's what we need to worry about this one. So this times that, need a little bit of work. So, but at first, you know that this is the anti-symmetric, so these two elements must be 0, right? And you can check that right away because this times that, this times that cancel, right? You see that, so we didn't make an error. And likewise, this is this times that, which is positive, and this times that, which is negative, and totally cancel. These two are 0. So we only have these two elements, and we just need one of them. The other is just negative. The other one. So if we work on this one, is gamma. So this times this one is this times that plus this times that, right? So this time that is both have the e sub x, and we have gamma square, both have gamma square, e sub x. The first one is just -1, right? The second one is beta square, right? But you know, gamma square is 1/1 minus beta square. So these two multiply to -1. Okay, you see that gamma square is 1/1 minus beta square. Right. That's right. Right. So this times that will be just -1. So we can actually right there. This minus E sub. And obviously, this will be E sub. You can check that one. This should work out. All right, so we got two of them done. Now you can do either one, this one or that one. So this one will be this times that plus this times that. This times that is just as difficult as we work out this. But this one is this times that plus this times that. And that is easy because this is zero. This is a copy. This one just copied this one. This is just identity matrix. So you just copy this down to here. Down there. That is easy. Down there. No, for that. Make sure you don't do copying error because there's lots of copying and sometimes you copy it wrong. All right, that's not too bad. Now the final, this one is just refracting this from this one. So this is 0, 1 to 0, 2 is 2, 0, 2, 0 is negative 2, 0. So it's this one, the negative, negative. E sub y minus beta E sub c. Okay, and this is 0, c is the negative 3, 0, which is this one. So minus beta E sub c plus beta E sub y. And this one is the negative, this one. Okay, minus beta E sub y. This one is the negative, this one. E sub y plus beta E sub c. Okay, now we got it all done. So this is the final form of this two multiplication. We got it. It's not too bad. I mean, but you don't want to do it every time you want the transformation because it still take a while to get to the final form. You want to get the formula. To get a formula, you realize this is this guy. This is the f pi. Okay, and f pi is just like f, except everything is pi. So you can compare elements by element and get the formula out. So like this element is the CO1 element, which is CO1 element. For pi, this becomes minus EX pi instead of EX minus EX pi. So minus EX pi and this element is minus EX. So it means EX pi is equal to EX. Okay, so the transformation is you have to write down EX pi equals EX. Okay, so that's easy. The parallel electric field doesn't change. The parallel component of electric field parallel to the relative velocity direction doesn't change. So that is easy. Now we can keep doing. So this is Ey pi is equals to whatever here. So down the Ey minus beta. Ey pi is this copy here down here. Y minus beta E sub c. Okay, just this one compare with this one with the pi. Okay, and likewise, this is EC pi. This ET. Okay, need to know what I'm doing. Just compare them. Yeah, let's do that. Okay, so that's not too bad, right? Now, for the magnetic field, now we look at other elements. So BX pi over here. And likewise, this is BX. So BX pi and BX, that's the same. So they are pi is BX. So that's like the same. That like the electric field, the parallel component of magnetic field also doesn't change. Okay, so that's okay. Now BY is this element. Let's compare with this element. So BY pi is down here. BY beta BC. Okay, and then finally it's BC. BC can either look at that or that one. So this one is BC. BC is just this one. BC. BC prime. BC minus beta. All right, so we finally get the formula that you can use. These two formula, you can use those. This should be easy to use also. 11.148 should be the same. Should be the same. Yeah, except Jackson used 1, 2, 3. I'm using XYZ. It doesn't matter. It's just 1, 2, 3 become XYZ. Okay. I think I got it. I got it right. Okay, we got it right. And then Jackson has this formula of, in vector form. This is in the component form, so you can transform the component accordingly. And but you can also write this as a vector. This is 3 vector. This is a spatial vector. So you can write it first, write down it first, and then check that the vector form is consistent with this component form. We'll look at that right away. Just write down beta with the velocity is just beta, the full beta. In this case, we are along x, but this is general direction beta. Okay, and then magnetic field. Minus square. Well, okay. Now we can see this. To see that these two are correct, you just compare this component by component with this transformation. Okay, like the EX component is the parallel component is EX, right? And this is EX. Look at the parallel component. The beta is in the parallel, so this two is perpendicular, so you don't have that. So compare this, the EX from this equation. Let's just write down here. So EX prime, check whether it's equals to gamma. This will give you EX. But this one, beta is in the x direction. So you have gamma squared, beta. And beta dot E will also give you an EX. You have extra beta as a beta squared. Gamma. Yeah. Okay. And to see that, you know that the gamma square beta square is gamma square minus, because obviously gamma square beta square is just gamma square multiplied by this one. Or you can just check it first, gamma square minus 1. Gamma square minus 1 is this minus 1. You take a common denominator. 1 minus 1 plus beta square. 1 minus 1 cancels. Beta square divided by 1 minus beta square, which is gamma square beta square. So this is the formula that we have a gamma square beta square. You can change that to gamma square minus 1, which is gamma plus 1 times gamma minus 1. So you cancel the gamma plus 1. So this is equals to gamma minus, this becomes gamma minus 1 times EX. And you see that that's exactly EX. Okay. So we check that. This is fine. For EY, this is in the X component, so you don't have this term, just have the cross product So let's check the EY prime. Whether so this is correct, and whether is equals to EY. And for this is an x component. So to get a y component, you need to x cos z, but that's x cos z is y, that's minus 1. So you have minus beta b sub c. And that's this one. Okay, so that's right. And likewise, EZ prime is down EZ. And again, you want C, this is X, this is X cos Y, we give you Z, but that is a positive sign. And this is this one. Let's check. Okay, so not too bad. And likewise, you can check the magnetic field, but another way to think about it is that these two transformation is exchanging B and E, and then change beta, change the sign of beta, right? But this term doesn't matter because you have beta squared, so change the signs. And likewise, this is just exchanging this transformation to this. You just exchange E and B and change beta to minus beta, right? So if you check these three, then this is also correct, right? So so you can say this is also valid, and you can use either one. You can use this set or this set. Depends on situation, which one is easier to use. Okay, and this is slightly more general because it's in vector form. You don't necessarily have to assign beta in any direction when you can test in the. But anyway, both of them you can use. It's okay. So any question? So the whole process is a little bit long, but the final product is not too difficult. All right.